All right. Hello, everyone. I'm so glad to be here when I have my slides. All right. So we proposed this talk to KubeCon North America. It was not selected. This is the first time I'm doing this session. If it works very well, we're going to hopefully do it at KubeCon Europe. So you're getting actually 2 for the price of 1 today. This is a never seen content before. As I was introduced, my name is Abdel. If you follow me, I am a little bit everywhere and nowhere all the time. This is my first trip in a 5 weeks back-to-back trip, which is going to take me a little bit around the world. This is the very busy season for developer advocates, typically. I have a lot of work going on. Yeah, I work at Google Cloud. I do Kubernetes. The reason I'm everywhere is because I'm the only Kubernetes developer advocate in Europe, actually, for Google. Google has 2 developer advocates for Kubernetes. That doesn't mean we're not serious about Kubernetes. It just means that no one cares at the company, except me and my colleague. You probably have heard my voice before at the Kubernetes podcast, right? Okay, So this is one of the weirdest things that happens to me is a lot of times people know my voice, but they don't know me. They don't know my face. But yeah, enough talking about me. Let's get into it. So let's talk a little bit about the basics of resource management. These are all stuff that you all should be familiar with, that you know. But I just want to walk you through some basics so we can all at the same level. You know, when you run stuff on Kubernetes, you can define what we call resource requests and limits, right? So resource requests are basically how much memory and CPU you want to allocate to your pods. You can't see the screen, right? What about now? It's good? OK, cool. Awesome. And then the limits are typically how much your pod can burst or scale up, right? The resource requests are typically an indication to the kubelet to find it's an indication to the scheduler first to find the node on which the pod will land. And then once the pod lands on the node, it's an indication to the kubelet to reserve a certain amount of resources on that node, right? So that's essentially what the kubelet can guarantee on the node. Typically, when you run a Kubernetes cluster, the kubelet will already assign a certain amount of resources for the system pods. So when you do something like kubectl describe a node, you will have 2 sets of resources. You have allocatable and available. So available is how much total CPU and memory is available on the node. Allocatable is the available minus what's reserved for things like daemon sets, login agents, service mesh agents, things of that nature, the kubelet itself, et cetera, et cetera. And same thing for memory. Now, how does that? One thing actually to keep in mind is that what I showed so far is at the container level. Starting Kubernetes 1.34 in beta, we introduce pod-level resource requests and limits. So not at the container level, but at the pod level. So this is actually a very useful feature for many reasons. One of the very simple use cases would be if you have a sidecar inside the pod. So you run a pod with 1 sidecar and 1 main container. The container is your application, and then the sidecar could be a login agent, for example. If your container itself is doing some compute cycles where it doesn't produce any logs, then it can burst into the available resources in the pod. So defining the resources at the pod level allows you to allow both containers to kind of burst up and down without being killed. Because the problem is that if you define very limited amount of resource requests and limits at the container levels, if one of them exceeds the resource requests, it might be killed, right? So by defining it at the pod level, you allow both containers to kind of burst up and down. So it could be that your main container is doing some in-memory computation, which doesn't produce logs, so the login agent doesn't have to do anything, but the main container can use the available memory in the pod. And vice versa. If the login agent is shipping logs outside, then it can actually use extra resources to be able to do its job. It's also useful for things like sidecars, for service mesh, for example. Same kind of use cases. So this is actually pretty new. Now, how does that translate at the container level? Well, CPU is basically a compressible resource, right? And the way CPU is allocated at the node is using this mechanism called cgroups in Linux. So that's typically a 250 milli CPU that you see there. OK, it doesn't work. 250 milli CPU translates into 256 shares, considering that one share is 1 core. So that's essentially 1/4 of a core. Then the limit, which is in this case 500 milli CPU, will translate into a quota. So that's essentially how much time the pod can exceed or can use extra time on the CPU, right? Memory is pretty straightforward. Memory is a fixed amount of resources in megabytes available. So the resources request will be set as request, and then the limit will be set as limit. And the key thing to keep in mind is that if a pod exceeds its resource requests in terms of CPU, the CPU is a compressible resource, so the pod will just run slower. If it exceeds memory, it will be killed, right? Good. So how do we right-size a pod? Good question. There are basically these three. This is my definition of quality of service. I know that Kubernetes doesn't really have a concept of QoS except priority. You can set pod priority, which allows the schedule to kill some pods to prioritize other pods. I think you have probably all guilty of using this mechanism to keep nodes running around, right? We have all done that? Good. So this is typically to solve the problem of fast autoscaling. If your cloud provider cannot give you nodes very fast, what you do is you create this thing we call balloon pods with low priority, just to keep certain nodes running. And then when your workload has to scale up, then Kubernetes will kill the low priority pods and then scale up your high priority pods. And hopefully by the time those scale up, then the cluster autoscaler, carpenter, whatever you want to call it, of your cloud provider had enough time to kick off autoscaling to add more nodes, right? So there is I categorize the quality of service in Kubernetes the following way. So guaranteed means basically you are setting your resource requests and limits to the same values. That basically just tells Kubernetes, I want this amount of resources to be available all the time. Burstable is when you set your limits to be higher than your requests. That allows the pod to burst up and down, right? And then best effort is YOLO mode. Like you don't set any request, resource, and limits, and then you just hope for the best, right? Finger crossed. So what happens when your pod is set to any of these quality of service classes, let's say? Guaranteed pods will always have the same amount of resources available all the time. So that's carved out from the node. Burstable means basically that the pod will be able to burst up into the available resources on the node. If another guaranteed pod comes in on that node, the amount of burstable resources will shrink down, up to the point where if the burstable pod actually exceeds the amount of resources available on the node, there will be a pressure on the node, and then the pod will be killed, right? So that's why I define those as quality of service, because burstable is really guaranteed is really guaranteeing that the pod will be running all the time. It will never be evicted, unless the node goes down or there are other reasons. So CPU, we talked about that. If you go over CPU, you'll be throttled. And so the question is there a way to handle resources dynamically? Is there a way to, like, today, you know that, well, today, that's what I'm going to talk about. But basically, up to Kubernetes 1.27, there was no way actually to resize pods, right? If you want to resize pods, you have to restart them. So can we handle resources more dynamically, easier? Well, one of the first features that was introduced to allow handling resources more dynamically is a feature that was added to 127 in alpha, and it's available in beta since 133, which is called In-Pod Resource Resize, IPPR. So In-Pod Resource Resize allows you to basically resize a pod live without restarting it. So it was introduced via a bunch of spec that was added to the pod definition, and it's of course available on the deployment definition. One of the first ones is this thing called resource policy, or resize policy. So resize policy allows you to define what happens when you resize each of the resources, CPU and memory, right? The second thing, of course, is the requests and the limits are now immutable, so you can change them. So before, if you do a kubectl edit on a pod and you try to change the resource request or limits, save, it will just revert the changes and tell you can do that. But now you can do it. And then you have the status field. So the status field actually allows you to track the status of a resize. So if you try to resize a pod and it's being resized, it will be in progress. And then once it's finished, it will be marked as done, right? Now, a question I get very often is, what happens if you try to resource a pod and there are not enough resources on the node? Well, nothing will happen. Kubernetes will try to resize it, but if there is no available resources on the node, the status field will be in progress forever until that pod gets killed and rescheduled somewhere else. Another question I get very often is, if I kubectl edit a pod and change its resource requests, and then it's stuck in progress because there is not enough resources on the node, and then at some point that pod gets evicted, rescheduled somewhere else, will it be rescheduled with the original resource requests or the modified resource requests or limits, right? Well, it's the original, because the source of truth is whatever you set in the first place. So when you change the resource requests and limits, the values are not going to be written into etcd until the status indicates ready. So if it's in progress, the limits values in etcd in the database will not change. But when the pod is done resizing, then the resource values will change in etcd. So what I'm trying to say here is basically kubectl patch or kubectl edit to change resources is not really a recommended way of doing it. Normally, you should go through your CI pipeline, change the YAML files or manifest, and then reapply them. In which case, the same thing will happen, whether you are doing a kubectl apply on an existing file or you are editing an existing pod, the pod is not going to be restarted. So in 1.233, so this is how it looks like. Essentially, you can do a kubectl patch on the pod, and then you can just basically supply a JSON, which is the spec on the container with the name of the container and the new resource requests. This is if you want to patch the pod live. But as I said, you can always change it through the manifest itself. I'm going a little bit too fast, so I need to slow down. So this actually creates a lot of very interesting possibilities, right? One of them would be the possibility to live resize a pod as it's running, or much more importantly, resize a pod during its startup time to speed up startup time. And here I'm talking to the Java developers in the room. Any Java developers around us? All right, few of you. Good, good. You're welcome. So Java workloads are very known for having this, sometimes, not all Java platforms, it depends really on the JVM, but let's say Spring Boot with the regular JVM, the standard JVM. Spring Boot will actually require more CPU cycles during startup time because it's doing lots of class calculation and optimizations and blah, 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 and all this kind of things, right? If you are working with Java native, like GraalVM, you're not going to see this problem because you don't have technically JVM. But like standard Java workload with JVM, it could benefit from having more resources at startup time, which will speed up the startup of the JVM application. So when this feature, which is the In-Place Pod Resize, was introduced in 1.27, me and the colleague, we actually wrote a controller. We don't recommend using it in production, although last time I was in a conference, somebody is actually running it in production. I don't recommend doing that. But we wrote a controller. Actually, I can show it to you. We called it Kube Startup CPU Boost. This was like just a proof of concept. And what this controller does, basically, it introduces this new CRD called Startup CPU Boost. And with the Startup CPU Boost, you have a selector. So you select which pod you want to target. And in the bottom, you have a policy. So you can, for example, say, I want to CPU boost by 50% up until the pod is ready. Which essentially, during the startup time, I just give the pod 50% more CPU. We could also do it based on time. So we could also have a fixed duration for the boost. So this allows us to basically give the pod more resources during startup time. And we did some tests with Spring Boot 3 application, and we could actually cut down the startup time of a standard Spring Boot application by 3. So it was a 3-factor in startup time. So it's something from 12 seconds to like 3 seconds. We did this because we wanted to experiment with it, and we did it also because we wanted to see if we can push this upstream. And it is happening today. So you're all familiar with vertical pod autoscaler. Basically, Kubernetes has 2 autoscaling mechanisms, HPA and VPA, right? VPA, up to today, has basically mainly 2 modes. There is an auto mode and an off mode, aka recommendation mode. When you write a VPA object, you also target a pod, so that's the target reference for which deployment do you want to vertically autoscale. And if you put it in update mode auto, when the pod needs more resources, it will just kill it and then create a new one, right? And if you put it on off, it's not going to kill the pod, but it will report recommendation in the status field. So when you do kubectl describe on the VPA object, and you go to the status part, it will tell you, OK, I think this pod should be set to this amount of resources. So these actually have been used by a lot of our customers, at least from Google side, to kind of get recommendations. So create a VPA in auto mode off, let it run for a few days. It collects a bunch of metrics, and then give you a better recommendation on how to resize your pod, right? So yeah, the current version of VPA, so up to 1.4, actually 1.3, sorry. So the API version 1.3, you have a pod, it needs to restart, kill it, and then create it. Now, in beta, starting 1.25, VPA is able actually to resize pods with a policy that tells it, do not restart the pod, right? So there is a new VPA version, which is 1. It was introduced in 1.4, and now it's 1.5. It's still in beta. But this new version allows us to basically set a policy at the VPA level to say, do not restart the pod. And so it looks like this. So a new update mode is introduced called In-Place or Recreate. So In-Place or Recreate basically means it will look at the restart policy or the resize policy at the pod level. I showed you that earlier. It will look at this here. You see the restart policy? And so for CPU, if it says not required, it will not restart it. And if it says required, it will restart it. So the new mode is in place or recreate, which is essentially basically means follow the policy set at the pod level. If the policy says restart, update without restarting, you do that. If it says restart, you do that. So this is new in 1.5. What is coming, this is still in alpha, is dynamic resource resize with ceiling. So this is not available yet, at least not in the current upstream version of VPA. This is a colleague of mine, Demo, a Googler. He's one of the contributors on this, but essentially what we want to do is we want to make this available upstream, which would allow you to basically set the mode to auto, and then set a minimum and maximum allowed. And that would allow the VPA to actually restart the pod, resize the pod up and down as it's running, with limits, of course. So the interesting thing here that they're working on is, and the reason why this is not upstream yet, is because we want to make sure that when we have min and max, then we can intelligently place the pod in a node that will allow us actually to go up to the max. Because if we only look at the amount of resources available right now, then there might be a situation where the VPA wants to resize the pod, but there is not enough resources available on the node, right? So what we want to do is we want to take into account the max, the ceiling, and then take that into account during scheduling so we can place the pod somewhere where those max amount of resources will be available so we can actually resize the pod intelligently. So, talked about that. Yeah, so essentially, the future is this, what we want to do. We want to be able to use VPA for both boosting the pod during the start cycle and also dynamically resizing it as it's running. So let me show you a quick demo of how that looks like. This is a demo using the CPU boost feature, which is available today. So I'm going to start it, and I'm going to pause it a few times to explain what you're looking at. So on the top corner, it's where we are doing kubectl apply. In the middle, we have a Spring Boot demo, and you will see it's ready state. Pay attention to the age and the restarts. In the bottom, it's the pod with all the requests and limits. In the third section, and the fourth section is the kubectl pod. Not very important. So, no, go back. Go back. Go back. Yes, here. All right, let's do this. So here, we kubectl applied Java Spring Boot application, and pay attention to here, ready and age. It's going to take roughly, I think it's 40 seconds or something to be ready. So up to where it says here, ready 1 out of 1, it's going to take roughly 40 seconds. Yeah, 42 seconds for the pod to be ready, roughly. Now, with CPU boost, so that's essentially applying a VPA, a vertical pod autoscaler, that has the CPU boost section defined. And that will take roughly 1/3 of the time. I think it takes like 12 seconds. And one thing you will notice here is that when we apply, so of course, this goes without saying, we have to apply the VPA object first. So you have to have the vertical pod autoscaler first, and then you deploy the pod, right? So it will take a few seconds for it to be ready, but notice here that those resource requests and limits are going to change. So now it's like 2 CPUs and as a request and 5 as a limit, and then it will drop down. So that's the boost in action, right? So we give the pod more resources at the beginning, and then when it's ready, and you can see here it takes roughly 13 seconds. So that's like 1/3 of the time, right? So this is already available starting VPA 1.5. You can use it. Now, one of the questions that I get also very often is compatibility with different programming languages, right? So we did a few tests. With Go, we can actually do a CPU and a memory resize live without impacting the application. I'm going to show you a quick demo here. It's not very high quality, but what you're looking at is on the right side, we just have a kubectl logs on this pod called memtest, Go memtest. It's just test memory, right? And it's going to be flickering all the time because it's a kubectl logs -f. So it's going to, like, as the logs are changing, it's going to, like, print. It's very verbose. And on the left side is the actual application. So here we have the pod running with, basically we have 125 megabytes of memory to start with. And so on the left side, I think we're going to do a kubectl describe, if I'm not mistaken. Let's see. Yeah, so we have, the pod has 700 megabytes of memory, and you see on the right side, it's roughly the same amount of memory, right? So now we're going to patch it and just change the memory, and then you should see on the right side that it will just get updated live. Yeah, so running a script to resize it, blah, blah, blah. And you can see already on the right side, it was resized. Like it was 900 megabits, and it was already gone to 1.2 gigabits. And we can also resize it down, by the way. So Go has this possibility of like live resizing the memory without impacting the application. And this is very important because since memory is not a compressible resource, resizing down is usually a problem depending on the kind of application, because you never know what's in a part of the memory, right? And you don't want necessarily to resize it down because you might kill the application. For Python, there is a partial support for memory resize. There is a possibility for you to restart the process itself without restart the app, and that will pick up the new amount of memory. But CPU is, of course, not a problem. Java, this is where it gets interesting. Java depends on the runtime. If you're running in Graal VM, so native Java application, it works. If you're running inside Spring, I think starting 3.4, 3.5, I don't remember the exact version, it actually works. So the JVM can pick up, because you set when you're starting a Java application, you have flags to set the memory, and usually you can either set the memory as a fixed amount, but since the new version of the Spring Boot, you can set the memory as a percentage of the available memory. So it's not a fixed amount, it's like a 75% or whatever. So you set that, so you leave memory for the garbage collector, but you also set the memory as a percentage of how much memory is available in the container. So if the container gets restarted, the Spring is aware of the container, so it can actually resize the memory up. C++ works, and Node.js also works. So these are just some kind of compatibility tests that we have done to kind of figure out if different programming languages can use this feature. I think that's all I had. I have 18 minutes left, so I can answer any questions. I hope that this was useful. I didn't expect that the next one was going to be my thank you slide. But so, with that, thank you so much. I hope this was useful. And that's my Linktree link if you want to find me on social media. And if you have any questions, I'm happy to answer them. Yes? Yeah. So the question is, how does that work with the network bandwidth? Because network bandwidth is CPU bound. So if you resize the CPU of a pod, will it get more bandwidth on the network? Is that the question?
That's broadly it, yeah.
Okay. Interesting. That's a very good question. I don't know. I can answer the question of the bandwidth, but I don't know about the static policy. I haven't tested it. But for the network policy, well, basically, when you're running cloud providers, usually your network bandwidth on the node is CPU bound, and it's usually a factor of how much cores you have on the node. So as long as your node has enough cores, Kubernetes will pick it up. So if you restart the pod, it will get more bandwidth, basically on the NIC. The only thing I would be careful about is that Kubernetes itself doesn't have a concept of quality of service between the pods on the node, right? So there is a risk that you might restart a pod and thinking, oh, there is enough resources available on the node, so I'm just going to restart this or resize this pod, give it more CPU. And giving it more CPU means it will start eating more bandwidth out of the node, and it might impact the other pods. Because Kubernetes doesn't have a way to prioritize network access based on which pod is priority. And so I did actually, this is a very good question. I did an interview recently with one of the, for the podcast, I did an interview for one of the networking SIG leads, Antonio Ojea. I don't know if you know him. He's like one of the people working on Kubernetes SIG networking. And he told me that they're trying to solve this problem with this thing called DRA, dynamic resource allocation. So with dynamic resource allocation, they are looking into being able to solve quality of service at the network using that. So in other terms, I can give you an example. Let's say you have a network-sensitive workload, AI or not AI, it doesn't matter, right? and you want that to be prioritized, and you want to deprioritize everything else, like login agents, metrics agents, whatever. So one of the ways you could do that is, since now, since few versions of Kubernetes, pods can have 2 network interfaces. So you could actually have one network interface dedicated for the traffic and one network interface dedicated for everything else. So that's one way you could do it, right? And they're looking into making that possible using dynamic resource allocation. Yeah. So the other solution is also to be able to assign specific IPs, to say this pod has this particular IP for this kind of traffic and this particular IP for this kind of traffic. So that's kind of how they're looking to solve this particular problem. I know we drifted away from your initial question, but it is all related, correct. All right, any other questions? Either this was very useful or no one had an idea what I was talking about for the last 30 minutes. Yes, of course.
Advantage of moving the limit of resources from container to pod level?
So as I explained earlier, one of the practical advantages is allowing the containers inside the pod to scale up and down without killing them. Because when you set the resource limits specifically at the container level, if one of the containers exceeds its limits, it will be killed and it will kill the entire pod.
Okay, so it can just hog the resources.
Correct. Yeah. So you set them at the pod level to say, okay, well, there is enough resources at the pod, and the 2 containers can just burst up and down. So the example I was giving earlier is my application is doing some in-memory stuff, so it needs more memory, but it's not logging or it's not shipping any metrics, so you don't really need to worry about the login agent or the metrics agent to ship logs out because it's not doing anything. So you allow the main container to burst up, basically.
Thank you.
That's one of the main use cases. Any other questions? Yes. Yeah. Yes. So this is what I showed so far is just one of the initial items of the roadmap of VPA. So the next is integrating VPA with DRA to scale GPUs, but it's quite difficult, yeah. Correct. So, but that has more to do with the way the GPU drivers, CUDA cores work rather than Kubernetes itself, right? There are plans up to the point if the GPU can support or the large language model, or not actually, it's not even the large language model, it's the inference engine. It's the thing that runs the model, like VLLM or Olama or whatever. That piece of software has to be able to scale up and down on extra GPUs, right? So one of the practical use cases for that would be able that you're running a model with a certain quantization, and then you want to change the quantization without restarting the model, right? So quantization is the value that defines the precision of the model, and it has a direct effect on how much memory the model consumes. So if you change quantization and you increase the value, then it needs more memory. So then if we can shard the model across 2 GPUs, if there are enough resources on the node, then that would be very useful. But that's multiple components that have to actually support this. Yes, yes. Yes, yes. Yeah, so that's one of the use cases. But the immediate thing on the roadmap for now is actually integrating VPA and HPA. So instead of choosing between scaling up or scaling out, you could just define a single autoscaler. We call it, it's basically a proprietary thing that we had on Google for a while, and we're trying to push it upstream. It's called multi-dimensional autoscaling, which essentially it's both horizontal and vertical, and this will intelligently either scale up or scale out depending on metrics, and you can kind of tweak it with policies. So that's the next roadmap for VPA, is to just make it closer to horizontal pod autoscaler. Make sense? All right, any other questions? Yes? To autoscale the quotas? To change the quotas? That's a very good question. I don't think it's on the roadmap, but I'm trying to think what would be a useful use case for that. So what you're saying is vertical vertical autoscaling for the namespace to like change quotas to allow the namespace to use more quotas, right? Well, so you can already do that by just like running VPA in off mode, and that will print out recommendations, right? So you can already do like just the current version, not even the new version of VPA, just like the existing stable version. Just run that in off mode, and then allow it to track the resources, and then extract those metrics to see what does the VPA recommend to do, right? So that would be one one way to do it. But the challenge there is that you will have to aggregate those at the namespace level. So there is no, to my knowledge, there is no open source solution to do that today. So we'll have to build something. Make sense? All right. Any other questions? If not, I would say thank you so much. Thanks for listening to me.